Welcome to our final module for the semester. In our previous module, we discussed the completeness theorem for first-order logic, which was a result of Kurt Gödel. 1 year later, Kurt Gödel was able to prove something called the incompleteness theorem, and it tells us what happens when we add in the axioms of piano arithmetic to our deductive system. Okay, so just a nice quick reminder of the axioms of piano arithmetic, which we'll refer to PA from this point forward. First off, the first axiom says that 0 is not the successor of any natural number. The second one tells us that the successor function is injective. In other words, we can subtract 1 from both sides of an equation and we preserve equality. 3 and 4 are the sort of recursive definition of addition. And basically the idea is that if you would like to add y to x, well, then you just repeatedly apply the successor function y many times to x. And then 5 and 6 tell us the iterative definition of multiplication. The idea being that if you multiply x times y, that's the same thing as adding up x to itself y many times. And then finally, we have axiom schema. So there's actually infinitely many different axioms. And it's true for every choice of well-formed formula Q with a single free variable x. And basically the idea is that if you could show the pieces of the sort of inductive argument here, in other words, that the well-formed formula is true of the base case, and that if it's true at x, it's true at the successor of x, then you're free to conclude that the formula is true for all possible natural numbers. And these are the axioms that we'll refer to when we're talking about piano arithmetic. And we'll be looking at some of the consequences of these various axioms in our next slides. So back when we were proving the completeness theorem for propositional logic in chapter 8, we introduced the notion of formal completeness and formal consistency. And I'll remind you of that here because we'll need this to state the incompleteness theorem for piano arithmetic. First off, let script T be a set of sentences in some first-order language. We'll be working in the language of arithmetic, but this could be any first-order language at all. We say that those set of sentences are formally complete if every sentence in the language we either have that T proves S or T proves the negation of S. And it's pretty easy to come up with some trivial examples of formally complete sets of sentences. Any set of sentences that are inconsistent. If you can derive a contradiction, well, then you can derive a proof of both S and the negation of S for any possible S. And so any inconsistent set of sentences automatically satisfies this definition of being formally complete. On the other hand, we'll be interested in collections that are consistent, and in that case, only one of those two options occurs. Either the set of sentences proves S, or if that doesn't happen, then it proves the negation of S. And it can't prove both of them in the case that it's a consistent collection of sentences. So we're now in a position to state the details of the incompleteness theorem, at least for the axiomatic systems of PA and ZF. As a reminder, ZF is the Zermelo-Fraenkel axioms for set theory that we established back in chapter 15. And it turns out that both of these axiomatic systems are not formally complete. In other words, there's sentences G and G prime, such that PA doesn't prove G and PA doesn't prove its negation. Nor does ZF prove G prime or its negation. Now, the incompleteness theorems also apply to lots of other axiomatic systems, and we'll say a bit more about that on our final slide and after we've proved the details of the incompleteness theorem for PA. Okay, so before we move on to the details of the proof of constructing G for our PA axioms, let me just give two examples of sentences in the language of arithmetic and then the language of set theory that are independent of PA and independent of ZF. Now, the proofs of these facts are a little more detailed than what we'll go through in our examples, but they give you a good sense that some of these sentences are not just sort of artifacts of the language, but in fact are statements that we would be interested in determining the truth value of. So, for example, the sentence con PA is the sentence that asserts the formal consistency of the PA axioms. That is, that there's no formal proof of a contradiction from the axioms of PA using our Fitch deductive system. In other words, PA doesn't prove the consistency of PA, and PA does not prove the negation of the consistency of PA. In fact, PA is just not strong enough to determine whether or not its own axioms are consistent. This also will turn out to be true of ZFC and pretty much any system that contains some copy or way of modeling the axioms of PA. On the other hand, the axiom of choice in ZF or in the language of set theory says that if you have a set A, all of whose members are non-empty, then there is a function which we'll denote by F, whose domain is that set A, which satisfies the following first order sentence. For every single element in A in the domain, f of x is an element of x. In other words, f of x picks out an element of the set x. We typically refer to this function f as a choice function, and hence the name, the axiom of choice. It turns out that the axioms of ZF are not enough to settle this question. So ZF does not prove the axiom of choice, nor does ZF prove the negation of the axiom of choice. Now, again, here we have a sentence which is sort of independent of ZF. Nonetheless, the axiom of choice is used throughout mathematics all over the place, especially in courses like algebra or a course in analysis, where you might use something like Zorn's lemma to construct a minimal or a maximal element. It's also used in analysis to construct the existence of a non-measurable set. And so it's an important sort of statement that is used in mathematics. And typically what's done is it's added on to the axioms of set theory. And we refer to it as the axiom of choice. And when we add on that axiom, instead of using the acronym ZF, we use the acronym ZFC. Okay, so that again gives you a good example of a sentence which is sort of independent of some of our axioms here, but also is important just from a mathematical perspective. Now, the sentence that we'll construct in our proof that's coming up in the next few slides here, that sentence G, will be a bit sort of convoluted and maybe could be some sort of artifact of the language itself. But these examples are intended to point out that even though it looks sort of like a somewhat convoluted definition, there are some natural examples of statements that are also independent of the axioms of PA and the axioms of ZF. Okay, so in order to prove the actual incompleteness theorem, we'll need to first discuss a key insight of Kurt-Gödel. And that's the idea that any of our well-formed formulas or our formal proofs can be encoded as a natural number. It turns out that there's many different ways of doing this encoding, but the key is that when you do the encoding, there is one and only one way to encode a given well-formed formula and a given formal proof. So let's talk about one way to do that. We'll consider the natural numbers in their base 10 format. So those are just sequences of the digits 0 through 9, finite sequences of the digits 0 through 9. But recall that you have to know a bit about addition and multiplication before you can even consider the base 10 format of a number, because remember, the digits tell you how many tens there are, how many hundreds, how many thousands, and so on and so forth. Luckily, our axioms of PA already have baked into them the definition of addition and multiplication. Now, what we'll do is we'll encode each one of our logical symbols first using a distinct natural number that doesn't contain 0 in base 10 form. And then we'll use the 0 to encode sequences of those symbols. Okay, so here I'm going to just make some arbitrary sort of identifications. And again, the idea is that they're distinct. You are free to choose them in whatever order you'd like. I'm going to first use the odd numbers. And when we get sort of that bottom line there and talk about variables, I'll say why we sort of skipped the even numbers. But first off, we'll encode negation with a 1, conjunction with a 3, disjunction with a 5, the conditional and biconditional with a 7 and 9, and then the universal and existential quantifiers with an 11 and 13. The reason I was skipping over the evens is that there are infinitely many variables, and we'll use the even numbers that don't contain a 0 in their base 10 expansion to represent our variables. So, for example, the first 5 variables, x1 through x5, are represented by the integers 2, 4, 6, 8. We skip 10 because it has a 0. 12 would be the next even number that doesn't have a 0, and so on and so forth. So again, we skip those that would have any zeros in them. So now that we've gotten through our logical symbols, we can move on to our predicates, constants, and function symbols. And here for addition, we'll use the number 15. For multiplication, we'll use the number 17. For the constant 0, we'll use the number 19. For the constant 1, we'll use the number 21. For the less than predicate, we use 23. The successor predicate, we'll use 25. And then finally, the identity predicate or the equality predicate will be represented with a 27. Let me point out again here that I've tried to bold out the constant symbols 0 and 1 because they're not actually the natural numbers 0 and 1, but instead just constant symbols within our first order language. And then finally, what we'll do with the 0 is the following. We'll let the number 0 represent the start of a new symbol. And what that allows us to do is then encode sequences of symbols or expressions, and in particular, well-formed formulas. So on the next slide, we'll go through a few examples of that. So here's just a handful of examples of well-formed formulas and their corresponding Gödel number. The first is an atomic sentence, which is just the constant symbol 1 is less than the constant symbol 0. And we would encode that first by writing 21. That's the number that represents the constant symbol 1. We would then put a 0 to indicate that's the end of that particular symbol. Then we would put 23. 23 is the number representing the less than predicate. We put another 0 to indicate that we're done with that particular symbol. And then finally, we end our Gödel number with a 19, which was the code for 0. So this nice sequence here codes in that 1 less than 0 sequence. And you can see that the zeros are just telling us when we are starting a new symbol. So for example, in the second line, you'll notice that the first part of that conjunction, 1 is less than 0, is the exact same expression that we had on the first line. And so there we'll have, again, that 21023019. So that would be that 1 is less than 0. Then we follow it by a 0 and a 3. 3, remember, was the symbol for the conjunction. And then a 0, and finally the expression for 1 plus 1 is equal to 1. And I'm not going to read that off, but you can see over there on the right that it goes through all of those details for 1 plus 1 is equal to, 1 plus 0 is equal to 1. Now, the third one has a universal quantifier and a variable. So we'll see our first even sort of number appearing in our list here. The for all quantifier, the universal quantifier, is encoded by 11. So we put an 11 first. Then we say we're done with that symbol, so we put in a 0. The variable x1 was denoted by the number 2, so we put a 2 and then a 0 to say that we're done with that particular symbol. Then we have a 1, which represents the negation. A 0 is saying we're moving on to the next symbol in our list. 25, remember, was the successor symbol. X1 was represented by 2, so we'd have a 0, 2, 0. 27 is the equality sign, and then finally 19 is the symbol for 0. And so this large number here in base 10 is, again, a unique representation of this well-formed formula you're seeing on the left. Now, in order to verify that you have the idea sort of down, you should pause the video for a moment and try to complete the Gödel number for this fourth row, that doubly universally quantified sentence. So here is the solution. First, we have that universal quantifier, so we'll get an 11. Then we have the variable x1, which is represented by a 2. We have another universal quantifier, that's an 11. The variable x2 is represented by a 4. Again, x1 is represented by a 2, equality is represented by 27, and then finally x2 is represented by 4. And in between each one of those sort of numbers, we should have placed a 0. So here we again have the Gödel numbering of this universally quantified statement. Now notice you can also encode the numbers of statements that are not well-formed formulas. Basically, any sort of sequence can be encoded in this sort of setup. And again, remember that it was a bit arbitrary what we chose for our coding, and we could have gone back and made different choices and obtained a different Gödel number. But the point is just that every well-formed formula is uniquely identified with some natural number, which is the case here. Now, before we jump into the details of the proof, let me point out that there's 2 ways to store the Gödel number. First, we'll use a hashtag P, and we'll color the font white to denote the actual Gödel number of P. And what we mean by that is just the regular old natural number in mathematics. On the other hand, we could also formally encode that number into the language of PA using our successor function. And that's where we'll use hashtag P, but in blue font. So that'll be the Gödel number of P in the language of PA using this successor function. So just to be clear, for example, hashtag conjunction would be the number 3. On the other, hashtag conjunction but colored in blue would be the expression successor, successor, successor of 0. And again, notice that one of them is in the language of PA and the other is just in terms of a number. Now, without making this distinction, it's a bit hard to parse through the next few arguments, but I'll try to color code them so that you can see where we're using the actual number in PA and where we're using the regular old sort of mathematical number for hashtag P. The second key insight of Kurt Gödel was the fixed point lemma, also called the diagonalization lemma in some textbooks. And the idea is that using the Gödel numbering, we can construct sentences in the language of arithmetic that reference themselves. So they say things about that actual sentence itself. Okay, so let's just say what the fixed point lemma says, and then we'll jump into a nice proof. So the fixed point lemma works for any well-formed formula in the language of arithmetic with one free variable. We'll call that well-formed formula P of x. It turns out that for every single one of those well-formed formulas with a single free variable, you can construct a sentence, which we're going to label C, which has the following property. Piano arithmetic proves that C is logically equivalent to P of hashtag C. And here again, hashtag C is that Gödel number, but being represented back in the language of arithmetic. And if you stare at that sentence for a moment and try to translate it back into English, what you find is that it's saying that C is equivalent to P of C. In other words, that sentence has the property expressed by P. In other words, we're sort of referencing the sentence C itself in the expression for C. The book skips over the details of this particular proof, but I'll sketch out a bit more of the content and point out where the difficulty lies, or what's difficult about this proof. The first thing that we'll do is construct a function from the natural numbers back to the natural numbers labeled by f. And the way that it works is if n is the Gödel number of some well-formed formula, q of x, with only one free variable x, then what we do is we first form the Gödel number of q in Peano arithmetic using our successor symbol. Then we plug that into q itself. So we replace that free variable x with that expression hashtag q written in the language of Peano arithmetic. Then, finally, what we do again is construct the Gödel number. And you'll notice that that sort of outer Gödel number is in white. So this is really just the natural number that represents this particular sentence. Now, if n doesn't represent a well-formed formula with one free variable, then we just output 0. And think about it as sort of a trash state that we're not going to be all that interested in. Now, the key insight of Gödel, and if we were really to work out the details of this, this would take us quite a bit of time, is that we can capture this function in the language of Peano arithmetic with a well-formed formula. And here I'm going to call that well-formed formula w of xy. And what I mean by capturing this particular function is the following. For every y, w of the Gödel number of q and y is true if and only if when we apply the function f to the Gödel number of q, we actually get back y. And here I've encoded in blue the sort of numbers here. These are natural numbers, but we have to encode them back into Peano arithmetic in terms of the successor symbols. But nonetheless, this is a fact that you can prove, and it has a bit to do with the fact that this function f is a computable function. But you're going to have to sort of just take it as a fact that this sentence can be proved. Now, if you stare at it for a moment, then you'll notice that f of the Gödel number of q is basically the Gödel number of the Gödel number of q. And here I've highlighted it in blue because now we're thinking about that f is being encoded into Peano arithmetic. Okay, so that universally quantified statement there at the bottom, we're going to sort of take as a statement that is granted. Again, the idea is that we can capture that function which we just defined back into the first order language of arithmetic. So now we can define a new well-formed formula called b of x. And this one we're going to base off of the predicate p of x that we had from the very start. Remember, we're trying to construct a fixed point for that well-formed formula p of x. Here we'll let b of x denote the following well-formed formula. For every y, w of xy implies p of y. Where this w of xy was the formula that captured that function f we defined on the previous slide. Now, what we do is we can construct our sentence C, which is going to be the fixed point, by taking b and plugging it into it, the Gödel number for b. And here that is highlighted in blue there. So that should be the Gödel number for b in the language of Peano arithmetic using the successor function. Now, if we just sort of plug it into that previous well-formed formula, we get the following. For every y, w of the Gödel number of b of y implies p of y. Now, from our previous slide, remember that w is capturing that function f. And so in this case, that is equivalent to the statement that y is equal to the Gödel number of the Gödel number of b. And again, this is all back in the formal language of piano arithmetic, where we're now representing those numbers using the successor function. And then finally, notice that we can just use equality introduction because we know that y is equal to the Gödel number of b evaluated at the Gödel number of b, and plug it right into that formula for p. And we find that that sentence is then equivalent to p of the Gödel number of c. So we started with that sentence C, and we found that it was equivalent to P of the Gödel number of C. And again, the P was taken to be an arbitrary well-formed formula with a free variable. And this sentence that we have is now referencing itself. So it's possible to write down some well-formed formulas in the language of arithmetic that now capture some of our logical notions. For example, it's possible to write down a well-formed formula, say p of x, with one single free variable x, such that when you replace that x with a natural number n, the resulting sentence is true if and only if that n represents the Gödel number of some well-formed formula, and it's false in all other cases. The same thing is true for recognizing if something is a well-formed formula with a single free variable, recognizing if something is in pre-mixed normal form, if something's an axiom, if something is a sentence with no free variables. And on the next couple of slides, we'll talk about how we can see if a sentence is a proof, if a sentence has a proof, and the most important sentence of all, this last one on the bottom, that a sentence has no proof. Okay, so once we apply the fixed point lemma to those well-formed formulas with a single variable, we get these following sentences. These are self-referential sentences. The first one says, this sentence is a well-formed formula. The second is, this sentence is a well-formed formula with a single free variable. The second one is clearly false because there's no free variable in that particular sentence, and a sentence can't have a free variable. The third one says, this sentence is in pre-mixed normal form. The fourth says, this sentence is an axiom of piano arithmetic, which is, again, obviously a false statement because that sentence is not one of the axioms that we established for piano arithmetic. The next one is, this sentence has no free variables. And clearly that is a true sentence because it doesn't have any free variables. Now, we can also create the sentences, this sentence is a proof, this sentence has a proof, and this sentence has no proof. And the final one of those sentences is going to be sort of the important piece of deriving our incompleteness sort of proof and finishing off the incompleteness theorem for piano arithmetic. The last sentence in our previous slide required us to say a bit about what a proof was in terms of a well-formed formula of piano arithmetic. Now, in order for that to actually work out, what we need to do is encode our actual proofs, not just our well-formed formulas, but our actual proofs in terms of Gödel numbers as well. And the process for that is fairly straightforward. So here on the screen, you're seeing the Gödel numbers for the well-formed formulas that we had looked at previously. And here, what I would like you to imagine is that this is perhaps an argument, with those first three well-formed formulas being the premises of the argument, and that last universally quantified statement there as being the conclusion of this particular argument. Now, what we'll do is we'll use a double zero to indicate the start of a new line, and a triple zero to separate the premises from the steps of the proof. In other words, triple zero is basically the Fitch bar. Now, Again, if the first three well-formed formulas are the premises and the last line is the conclusion, then we could encode that entire argument into a single number called the Gödel number of that particular argument. Now, the way it works is you first write down the Gödel number for 1 is less than 0. Then we say, okay, we're going on to a new line, so we put 2 zeros. And here I've bolded out those double zeros and put a space just to make it a little bit more readable. You then write down that second well-formed formula in terms of its Gödel number, and then 2 zeros. The third sentence in terms of its Gödel number, and then finally 3 zeros. The 3 zeros, again, indicate that you're done with listing the premises of your argument. And then you list off the conclusion. And if we were doing a proof, we would also include any of the intermediate steps, and the new lines would be constructed from just a double zero again. So here again is a nice way of encoding not just the sentences and well-formed formulas of the language, but actually the proofs and the arguments of the language as well. So let's be a bit more precise and write down the actual well-formed formula with a single free variable that will apply the fixed point lemma to. First off, we'll have to start with something that requires quite a bit of detail. And if you read a textbook that covers the incompleteness theorem in all of its detail, then you'll find that this will take a couple of chapters to sort of get through. So we'll just sort of take it as an assumption here and work from there. And it's the following sort of fact. With our coding that we use to encode our arguments, we can write down a well-formed formula with two free variables, in this case n and m. I'm going to call it prove nm. That is equivalent to the following English statement. N is the Gödel code for a proof whose premises are only axioms of piano arithmetic, and whose last line is a code for the statement M. And that allows us to write down a new well-formed formula called proof X in the following way. There exists a Y such that prove YX. In other words, Y is a proof of X. And so that well-formed formula proof X with a single free variable is saying that there is a proof of the statement X. And again, this is a well-formed formula in the language of piano arithmetic. So here the X is ranging over the natural numbers. And what it's saying is that if you plug in a natural number, then that particular statement will be true if there really is a proof of the sentence coded by that particular natural number. And if either that sentence doesn't code if that natural number doesn't code a sentence, or there is no proof that exists, then it's marked as false. And if we apply the fixed point theorem to proof X, we get our sentence G that we alluded to at the very beginning of this presentation. And we find that piano arithmetic proves that G is true if and only if the negation of proof is true for the Gödel number of G. Now, if we translate this just back into English, what this says is that this sentence has no proof. Okay, so let's finish off the argument, and let's show that if piano arithmetic is consistent, then piano arithmetic can't prove G, and it can't prove its negation. In other words, PA is incomplete. First off, if this sentence G were false, then it would mean that piano arithmetic proved G. Now, because our Fitch deductive system is sound, and we're assuming that all of our axioms of PA are true, that would mean that the sentence G was true as well. But that would be a contradiction. And since we're assuming that PA is consistent, our initial assumption must have been false. In other words, G must be true, and by the very nature of what it says, that means that piano arithmetic can't prove G. Now, since the sentence G is true, that means the negation of G is false, and again, because Fitch is a sound system, piano arithmetic won't be able to prove this false statement, negation of G. In either case, we have that piano arithmetic can't prove G, and piano arithmetic can't prove the negation of G. Two important questions arise after students are exposed to this proof. First, can we remove the assumption that piano arithmetic is consistent from the argument? And second, what happens if we use a different Gödel numbering? It was sort of arbitrary what we were picking for our encoding, and if we picked a different encoding, would we get a different sentence G and a different Gödel sentence that was showing the incompleteness of piano arithmetic? Now, the answer to those two questions are the following. One, we cannot remove the assumption about the consistency of PA. And two, it does not matter what method we use for numbering the sentences. It turns out that you can prove that they're all equivalent to one another. In fact, you can prove a bit more. You can show that they're all equivalent to the consistency of PA itself. So this self-recursive sentence G that was built up from our Gödel numbering is really just a convoluted way of saying that piano arithmetic is consistent. So let's go ahead and just talk a bit about what the proof looks like. First off, in our previous slide, we showed that if piano arithmetic was consistent, then the sentence G had to be true. So we've got one direction of that biconditional. Now, suppose that G is true. Now, if G is true, then by what it asserts, it means that there is no proof of G. Remember, G is the sentence that says, this sentence has no proof. Now, if that sentence doesn't have a proof, well then piano arithmetic has to be consistent, because if it was inconsistent, it would prove all possible sentences. Remember, by the principle of explosion, if we can get to a contradiction, then we can prove any sentence at all. So the mere fact that G is true tells us that piano arithmetic has to be consistent. And that's the proof of the if and only if. So if we then sort of plug that back into the sentence we had on the previous slide, what we find is that PA can't prove the consistency of PA. And furthermore, PA can't prove the negation of the consistency of PA. And that's because the consistency of PA is already logically equivalent to a sentence that PA couldn't prove and that PA couldn't prove its negation. Now, you might be thinking that the situation is similar to what we did for the axiom of choice. Perhaps we just have to throw in the consistency of PA as an axiom of PA. But it turns out that that particular system can then go through the same process that we did, encoding the Gödel sentences and constructing a new sentence G. And there again, that new sentence G that we produce will be equivalent to the consistency of PA plus the consistency of PA. And again, that is an incomplete theory. And you can add that as an axiom and so on and so forth. But there's really never an end in sight. And in fact, you can always, as long as you have this sort of copy of PA sitting inside your logical apparatus, re-go through this entire Gödel sentencing sort of process and build up this recursive sentence G that says it has no proof. So just to emphasize that last point, if we work with a stronger axiomatic theory, like for example ZF, where we can encode the natural numbers and show that the axioms of piano arithmetic are sort of simulated there. So we have sort of a copy of piano arithmetic within our axiomatic system ZF. Then we can carry out the entire argument that we just did. We just have to include all of the logical apparatus for ZF and not just PA. So we'd have to look at the language of ZF and make sure that we had a way of encoding all of the proofs and all of the well-formed formulas. But nonetheless, that process would be exactly the same. And because we had the natural numbers encoded within ZF, we could go through the full diagonalization argument and construct these sentences in ZF that are sort of self-referential, that reference themselves. And in particular, you could show that
the consistency of ZF is equivalent to this Gödel sentence, just like we did for piano arithmetic. And that then tells you that ZF can't prove its own consistency, and it can't prove the negation of its own consistency. And the same story is true for any axiomatic system that we might construct that contains a copy of piano arithmetic. And if we're going to have a foundation of mathematics, it better include that. So really, any foundation for mathematics that we can write down will not be able to prove its own consistency, and furthermore, won't be able to prove its negation of its consistency.